Hello, hello. Testing the mic first before we start the session today. All right. So I think we can begin. Everybody looks quite excited in chat. All right, fantastic. Let's begin today's session. So hang on a second. Right, all clear, all looking good. So hi, welcome back to today's session. I am Zong Yang, and it's been a week since our previous session. I apologize for our slight mic issues last time. I hope today you can hear us loud and clear. All right. So without further ado, today we are going through IGCSE Physics, subject code 0625, winter 2025, paper 4, set 3. All right, so as per usual, we'll be going through the entire question paper and we are going to solve each question in detail. So I also hope everybody will find this session useful. So also please do take note, right? We'll be answering 15 appropriate questions from the live comment section, which means the chat over there. You guys can ask at most 15 relevant questions, and this will be answered by none other than our fantastic tutor over here, Mr. Narayan sir, and they will be vetted by him. So the questions will be in a first come, first serve basis. So if you have any questions, please submit them through the chat, okay? Right, so today we'll be going through paper 4, and paper 4 is the extended part of the IGCSE papers. So for those of you guys who wants the core paper, unfortunately we will not be going through them. We'll be going through paper 4 for the more difficult questions. Yeah, all right. Now, without further ado, let's begin today's paper. All right, now for first thing first, please take note, right, that when we are solving papers, right, the weight of 1 kilogram is 9.8. So essentially, G is equal to 9.8 meters per second squared. Okay, so if we were to randomly pull, G out from somewhere, it's from here. Okay, so G is 9.8. Huh? Okay, and all the more arithmetic stuff, like those big calculations, I will key everything in my calculator and it will be solved right there. Okay, now without further ado, let's move on. Right, don't mind the Pikachu here, he's your part of your tutor today. All right, so we are here at our first question. All right, so question 1. Okay, question 1 shows a hard ball dropped vertically downwards, right? And this figure, this graph over here, shows a speed time graph for the ball when it's dropped until it hits the ground. Take note, right? This is the speed time graph. So speed is in the y-axis, which is meter per second, and time in seconds is on the x-axis. So remember, this is a speed time graph, not a velocity time graph, not a distance time graph, speed time graph, okay? Yeah. So for this question, air resistance is ignored. So that is a big sigh of relief for most of you guys down here. So for this graph over here, we are to start with A part 1 for the question. which is to describe the motion of the ball in figure 1.1. All right. Let's take a look at the ball over here, the graph over here. So as you can see, this is a nice straight line, okay? A nice straight line in the speed time graph, right? And this line is actually moving upwards. It has a positive gradient. Means it goes upwards like this, all right? If it's a negative gradient, it goes downwards this way instead, okay? Oops. Yeah, if it's negative gradient, it should go downwards this way. Now, we see over here, right? The ball starts at 0 time, 0 seconds at 0 speed. And over here, this is 0.6 seconds. And it moves at a speed of this here. So what is this? Okay. So over here, you can see this is 4, 5, 6, 7, 8. So over here, this is 5, right? And where is this graph stop over here? This is this is in divisions of 0.2. So it's 5.2, 5.4, 5.6, 5.8, and 6.0. Between 5.8 and 6.0, this is 5.9 over here. Okay? So let's describe the motion of the ball. Okay? The ball actually moves upwards at this is not constant speed, this is actually a constant acceleration. Okay, so let's do this. The ball has a constant acceleration. Okay, so as long as you write constant acceleration, you get your full 1 mark over here. Okay, yeah. So just now we have found out, right, the graph stops here at 5.9 meters per second at time 0.6 seconds. Okay, so in part 2, we have to find the distance that we have to prove that the distance traveled by the ball is 1.8 meters. Okay, so as you do remember from our calculations for speed time calculations, right? We can see over here, max speed here is equal to 5.9 meters per second. Okay, and the time taken for this maximum speed is 0.6 seconds. Okay, so when we want to find the distance traveled, we find this area under the graph over here up to here. Okay, all the way up to here. So to find this area, we take the area of a triangle, which is, if you remember, half times the base over here times the height. Okay, so the base is 0.6, the height is 5.9. So let's do it this time round. Okay, distance traveled is equals to the area under graph. This gives you your first mark, okay, which is equals to half times the base, which is 0.6, multiplied by 5.9, which is the maximum speed we have over here. All right? Now, let's key this into a calculator, and you will get, okay, 1.77 meters, right? But of course, we want to make sure this is in 2 significant figures. So let's do the round up to, you see over here, this is 7. 7 is greater than 5. So this 7 becomes 8. So it's 1.8 meters. Okay, in 2 significant figures, which is equal to right here, the 1.8 over here. Okay, good. Right, so this is part 2. Done. Oh dear, I think I should move this a little bit away so you guys can see. All right, that's a little bit better. let's move on with our question, with A part 3. All right, so the mass of the ball is 0.54 kilograms. So we are to calculate the gravitational potential energy stored in the ball before it is dropped. Okay, so since you can see, right, the ball has traveled 1.8 meters and the ball drops a total distance of 1.8 meters. So this is our change in height. Okay, we have the mass over here. Okay, and as you know, gravitational potential energy is equals to mass times gravitational constant times the height. So as you remember just now, G is equal to 9.8 meters per second squared. So let's use that in as well. Okay, mass over here is 0.54 multiplied by 9.8 meters per second squared and multiplied by what we have over here, 1.8 meters. Okay, and that, plugging into the calculators, you should get 9.5256, so on and so forth. And let's turn this into two significant figures as per usual. You see, two significant figures, 9, 5. So first significant figure, second significant figure, and let's take a look at this. 2 is less than 5, so we round down to 9.5. And the unit for energy is joules. So let's write this down. Okay. Please remember to write down the units. That will make sure you have a good, the full 2 marks. All right. So just now, we have saw, right? When you write this equation down, you get your 1 mark. And when you get this correct, you get your 2nd mark. Okay? So far so good, yeah? All right. Also, just before I forget, I want to quickly go back to part 2. So back here, right, we noted that the distance traveled is area under graph, and I did say this gives you your first mark. And writing this down, half times 0.6 times 5.9, that gives you your 2nd mark to give you your full 2 marks. Okay? And with that done, we have our first 5 marks for this question done. Let's move on. Okay. Now, A part 4. Determine the kinetic energy of the ball when it has fallen halfway to the ground. So, this is the ball, right? It falls a total distance of, as we remember, 1.8 meters. Am I right to say that? Okay. So 1.8 meters, it falls. So halfway, it's 0.9, isn't it? From the ground. Okay. So basically, when you're halfway towards the ground, right, half of your gravitational potential energy is converted into kinetic energy. So the energy that is converted is also halved. Okay. So the kinetic energy of the ball is simply half of the GPE. Oops. My bad. Half of the GPE of the ball, and which is half times, as we have seen just now, 9.5. And that gets you 4.75, which in 2 significant figures, you get 4.8 joules to SF. Okay, as we've seen here, 5 is equal to or greater than 5, so we round upwards. So 4.7 becomes 4.8. Okay, right? So there you go. That's how you get this answer. So far, so good, yeah? Okay. Right, let's move on to part B. Question 1, part B. All right, so now we have something slightly that is more extreme for some reason. So the ball is dropped from an airplane. Okay, and air resistance acts on the ball. So we want to explain how the vertical motion of the ball changes from when it's just drop to just before it hits the ground. So it will hit the ground later, and for this, air resistance is now part of the equation. So let's try to answer this as the best we can. Okay? So basically, as you do know, when the ball is dropped from the airplane, right, the initial speed when it first drops here is 0 meter per second over here. So of course the airplane is moving at this speed right here, but we want to consider only the vertical speed of the ball, not the horizontal speed. Okay, so when the ball first drops, it is moving at 0 meters per second. It's not moving, right? When it first you throw the ball out of the airplane. Okay, and then during this time, right, it undergoes something called gravity. It's affected by gravity. So during this time, when there is no speed, the force of gravity is much greater than the force of air resistance. Okay. Now, as the ball keeps moving further, keeps dropping down, right, it increases in speed. Okay. And when the ball increases in speed, air resistance also increases. But now, before it hits the ground, right, it should be moving at its maximum speed. Okay? During this time, right, air resistance has reached its maximum, and we should say that this is something called, it should be going through something called, terminal velocity. That means this speed is now constant. When speed is constant, there is no acceleration, there is no force, there is no resultant force acting on the ball. So during this time, right, the force of gravity should be equal to the force of air resistance. Okay? Right. So let's just write it down one step at a time. Okay? Let me just write this down over here. Okay. So initially, Initially, when the ball drops, right, gravitational force acting downwards is much higher than its air resistance, which accelerates the ball downwards. Okay, this is our first mark that's required. Okay, now secondly, let's type here as the as the ball, okay, speeds up, okay, air resistance increases. All right, until it is equal in magnitude of the gravitational force. Okay, this is our second mark. Right? Okay, very good. Let me just move this here nicely. Wow, what is wrong with this? That's hilarious. Okay, last but not least, this reduces acceleration until the ball reaches constant speed as terminal velocity until it hits the ground. And that's your third mark. Okay. Right, there we go. So this is a 3-mark question. So first mark, you'll get it when you say that, right, gravitational force acting downwards is much higher than air resistance, and this accelerates the ball downwards. That gets you your first mark. Okay. Second mark you get it when you mention the ball speeds up, air resistance increases until it is the equal magnitude of the gravitational force. That's the second mark. Your third mark is when you write this reduced acceleration until the ball reaches constant speed as terminal velocity. That's your full 3 marks. Okay. All right, that's good. Now, this is the large question done. 3 marks obtained. Pretty easy, yeah? Good. Now, let's move on to part C. Wow, we can make so many questions from just one ball dropping off height, yeah? Okay. But please don't do this at home, yeah? Don't throw your ball off a balcony. This is bad bad neighbor behavior. Okay. Right, so let's go to part C. Right, a softball is dropped by a student so it bounces on the ground. And this figure over here, figure 1.2, shows the height and time graph for the ball. Okay, the height is measured from the ground and the ball bounces 4 times. 1, 2, 3, and 4. Okay, the 5th time we don't count, yeah? So we are to explain why there's a change of height between B and C. The change of height between the ball between B and C is less than the change in height between A and B. Right, so what does this mean, right? So as you can see here, A and B, right, there's a big height over here. As C and B over here, right, this is much shorter than height AB. Why is this so? Okay, why is this so? All right, so the first thing you will know is that the question did mention the ball is soft. So when a ball that's soft hits the ground, right, it changes in shape, doesn't it? Right? So when it changes its shape, what is dissipated off is energy. So what that means is some energy is lost. So when from A to B, is GPE is maximum here, gravitational potential energy is the most over here, and over at B, kinetic energy is the maximum. But when the ball hits the floor over here, some of this kinetic energy is converted into heat and sound energy. So there is less energy to convert back into gravitational potential energy in C. All right, so with that explanation, let's write down the answer. Where is my typing? There we go. So, as you can see, when the ball hits the ground, some of the kinetic energy is converted into sound and heat energy to the surroundings. Okay, this is our first mark out of the 2 we are getting. Okay, so pardon my terrible typing. Let's leave it here. All right, this is our first mark. Thus, the ball has less kinetic energy after hitting the ground and less energy is converted into gravitational potential energy in C compared to A. And that is your second mark. Okay, pretty straightforward, pretty easy, yeah, isn't it? All right, so 2 marks, just like that. Okay, so 2 marks, this is your first mark, this is your second mark. Oh, all right. Yoink. Okay, now we are done with question 1. Look, a total of 11 marks in the bag, just like that. Pretty easy, isn't it? Right? Okay, fantastic. Wow, we have so many students. We have students from all over the world. I'm glad that you guys are joining us. Thank you for joining us and listening to our little lecture over here. Hope you guys are having a good time, yeah? All right. So Once that's done, we can move on to question 2. All right, let's go to question 2. Oh, we have another ball-related question. This Cambridge question, this paper setter must be an athlete of some sort, yeah? All right, so anyway, lame jokes aside, let's go to question 2. So a cricket ball is traveling at a speed of 25 meters per second horizontally through the air, and the mass of the ball is 0.14 kg. So it's a ball traveling horizontally 25 meters per second and has a mass of 0.14 kg. Okay, and a player catches the ball and it comes to rest. So we are to calculate the change in momentum in part A during the catch. So what exactly is momentum? As you remember, momentum, or we call it P in physics, is equal to the change, is equals to the mass multiplied by the velocity, right? So a change in momentum is, since the mass is the same, it's equals to the mass multiplied by the change in velocity. So let's write that down, okay? So change in velocity, change in momentum is equals to the mass of the ball multiplied by the change in velocity. So the change of velocity, as you can see here, is 25 meters per second, and it goes to rest, which is 0 when it goes to rest. So we can calculate like this, and the mass is 0.14 kg multiplied by 25 meters per second minus 0 meters per second because it came to rest, and that, after some multiplications, you should get this, okay? 3.5, right? Kilograms per meters per second, okay? Please remember to write this down for your units, okay? Kilograms is the unit for mass, and meter per second is the unit for velocity. So let's write that down, okay? Right, so 3.5 kg meter per second, okay? You can also write it in this way, oops, kg meter per second. This is the same thing, okay? This is the more scientific method. I prefer the writing like this, but this is accepted as well, okay? So how do you get your full 2 marks? Your first mark comes from writing that, mass is equals to the change in momentum is equals to mass times the change in velocity, and this gives you your first mark. The second mark comes from the correct answer, okay? Very good. Now, let's go to part B, part B, okay? The player's hands, okay, his hands are in contact with the ball, for the moving ball, right, for 9.7 milliseconds, okay? So we have to calculate the horizontal force exerted by her hands to bring the ball to a rest, okay? So now we have given that the moving ball is in contact with the hands for 9.7 milliseconds. Oh, this is something to do with impulse, for a change in momentum and impulse, right? So let's use this method, all right? So if you remember correctly, right, force is equals to the change in momentum, right, divided by the change in time, okay? Remember this, right? Force is equal to change in momentum divided by the change in time. This is the equation for force as well, all right? If you remember, F is equals to ma, right? And then ma is equals to mass times velocity over time. So this is also an application of this, okay? Force equals to mass times acceleration is also equals to mass times velocity divided by time. And mass times velocity is momentum, okay? So change in momentum, right? So we have seen just now the change in momentum, oops, my bad, as we've seen up here, is 3.5 kilograms 3.5 kilograms meter per second. So let's write down 3.5 over here on top. Divide by change in time, which is 9.7 milliseconds. 9.7 milliseconds is equals to 0.0097 seconds. Okay? So remember, this is the unit of kg meter second per second. Okay? Now let's do the calculations. And we key that into the calculator. It will be equals to 360.82 . This is in newtons, by the way. And now let's convert this into two significant figures. So the first two figures, 3 and 6, and the third figure, 0, is smaller than 5, so we round everything downwards. And thus, we get 360, okay, newtons in two significant figures. All right, 360 no scope, yeah? Fantastic. Okay, good. And with that done, we have this question is worth about 3 marks. So how do we get the full 3 marks? Right, so firstly, right, the first mark is given when you write down force is equals to change in momentum divided by change in time. This is your first mark, okay? Your second mark is given, right, when you put in the correct number for the change in momentum, which is 3.5, divided by 0.0097. This is your second mark, okay? And third mark, of course, is for the correct answer to give you your full 3 marks. All right? So pretty straightforward. I know most people will not think of this because, the whole thing about force and impulse and that sort of thing is a little bit confusing, even for me as a student back then. So if you can remember your basics, this should be fine, okay? So if this is a problem for you guys, please practice more papers. Please look for a teacher to help you to solve the questions together. And I think you'll be fine after quite a lot of practices. At the same time, I think just to, plug our system up, we are Homeschool.Asia. We have videos to teach you how to solve these kind of questions. And we also have videos to teach you all you need to do for your basics for momentum, time. I can even tell you the video is 1.22 in our IGCSE Physics videos. So now at break over, if you guys have any other questions so far, please feel free to ask our friendly teacher, Mr. Narayan sir, in chat over there, okay? So let me take a look at chat to see what you guys are up to, right? So, okay, looking pretty good. If you guys have any questions, please feel free to ask Narayan sir, and we will stop to take a look at some questions if you have any, okay? If no questions, we can move on to question 3 for this paper. Fantastic, no questions. All right. Okay, thank you, Narayan sir. There's so far no questions. So without further ado, let's move on to question 3. All right. So question 3 wants you to solve something called a Sankey diagram. Okay. So a Sankey diagram is pretty straightforward. This is the power input. And usually the arrow that points straight to the right is the useful power output. Any arrow that points downwards like this is wasted power. All right, so energy that's wasted, let's say in turning turbine, energy wasted due to heat, so on and so forth. Okay, so this is a power transfer from a coal-fired power station. Okay, and as you can see here, the input here is 3,400 megawatts, and there's a useful power output here that we are supposed to calculate. And down here you can see, right, there's power wasted due to thermal energy transfers, 22,200 and 2,200 megawatts. Power used in the power station, 40 megawatts, and power used in transmission, 25 megawatts. So, firstly first, we are to show that the useful power output from the power station is approximately 1,100 megawatts. All right, so over here, this is the power input. So power output, power output is equals to our input minus all the wasted energy. Wasted power, okay? Sorry, not energy, wasted power. And there goes 3400 megawatts minus, okay, 2200 minus 40 and minus 25. So, doing the maths, you should get 1135 megawatts as your answer. But hey, hang on a minute. You have to show that it is 1100 megawatts. And to do that, you have to convert this into two significant figures as per usual. So, over here, 3 is the number you want to see, and 3 is lower than 5. So we round down the number to 1100 megawatts. Two significant figures. Easy, right? So, as long as you write down power output is equal to power input minus wasted power, you get 1 mark here. And then you getting this and two significant figures is another mark here. So that gets you your full 2 marks. Okay? This is very simple so far, isn't it? Right, so let's move on. Okay. Oh, I have a question. We have a question here. Right, is this stream useful for O-level answers? This is for the IGCSE, so the international GCEs. So although the topics here might not be similar to your O-levels, I think most of them should be quite useful. So you can tune in to stay in and listen to us if you feel like it. Yeah? All right, so let's move on. Okay, so for A part 2, we are to calculate the power efficiency of the power station. So, as you do remember, efficiency is equal to the power output, all right? The used power output divided by the power input and multiply this by 100%. Okay, doing this will get you your first mark. Okay, now let's do the calculations. The power output, as we calculated before, is 1100 megawatts divided by the power input of 3400. Okay, and multiply by 100%. And you should get about 32.352 yada yada percent. And doing the standard 2 sig fig, you should get 32% efficiency, right? So finding this answer should get you your second mark. Okay, so please remember to write efficiency in percentage. Okay, this is very, very important. Oh, okay, yeah. Okay, right. Now let's move on to part B of this question. Describe how useful energy may be obtained from geothermal resources. Okay, right, so first things first, what exactly is geothermal resources, right? So geothermal resources, first thing you think of is a volcano, isn't it? Right? Not quite actually. So geothermal resources, right, is basically the heated rocks underneath the Earth's surface, right? This is very hot down here, okay? And what we do is, we as humans, we are kind of smart. We build power stations, right? We pump water into this hot rocks down here, heat it up, turns into steam, the steam rises back up, turns the generator up here, and we generate electricity. Pretty straightforward, isn't it? So let's write down what exactly happens in a geothermal power station. Okay, so first thing first, let's turn this into our text again. Okay. Okay, so water is pumped into the ground that is to be heated by hot rocks, which turns the water into steam. Okay, this is your first mark. All right. And your second mark should be written like this. This steam then, moves back up to the surface to turn a generator to produce electricity. That is your second mark. Yeah, very straightforward, isn't it? Very easy, yeah? So I hope this diagram kind of helps, yeah? Okay, for those more visual learners out there, okay? So if you want to, revise on your power sources and stuff like that, please check out Homeschool.asia's IGCSE Physics syllabus. This is exactly video 1.26, okay? Yeah. All right, let's move on. All good, yeah? So let's move on to question 4. All right, question 4. We have a rectangular glass tank that contains 3.0 meter cube of liquid, and the mass of the liquid is 2,800 kilograms. So we have to calculate the density of the liquid. So density, if you remember, the symbol for it is actually something called rho. Okay, and density is equal to the mass of the object, or say in this case the liquid, divided by the total volume of the liquid. Okay, and so we already have the mass, which is 2,800 kilograms, and the volume, which is 3.0 meter cube. Very, very fast, right? 2,800 kilograms divided by 3.0, which is the volume, and that should give you 933.33333, and so on. Okay, and now let's just do your standard two simple figures. So 3 is the first two. The third number 3 is lower than 5, so we round everything downwards. We get 930. All right, this is meter cube, this is kg, so kg per meter cube. Okay, so to get your 2 mark, this is a 1 mark question. Okay, so if you manage to get this, you manage to get this number, is your 1 mark. Okay, 930 kg per meter cube. Please remember to write your units properly, okay? This is very important, and this can actually make you lose your mark. All right? Good. Now, let's move on to part 2 of this question, okay? Part 2 of part 4A, all right? So 4A part 2, a metal block is placed in the tank and it sinks into the bottom. And the top surface of the block is 1.1 meters above the surface of the liquid. So what do you mean the top surface? Is this part over here is 1.1 meters, okay, below the surface of the liquid. So we see this whole tank over here. And we want to find out what's the force exerted by the liquid on top of this block over here. Okay? There are 2 methods to solve this question. I will only show the first method. The second method, you can find it from our downloadable sources later once my team has prepared the PDF for this document. Okay, so let's find out method number 1. So the first method is actually really straightforward also. So we want to first calculate the pressure exerted to the metal block surface, and then we calculate the force exerted. Okay, so first things first, let's calculate the pressure exerted to this metal block surface over here. So as you can see, the metal block is 1.1 meters. The surface of this metal block is 1.1 meters below this liquid, okay? So we're taking this entire chunk right here. So pressure due to the liquid, okay? If you remember, it is height multiplied by density of the liquid multiplied by gravitational constant, G, H rho G, okay? Now, let's find out what are all these numbers, okay? H, as we know earlier, is 1.1 meters. So 1.1 multiplied by rho. Where do you get this rho again? Right here. It's the same liquid, right? So rho over here, as we measured before, is 930. Okay, 930 multiplied by G. G, as we have said before, G is equals to 9.8 meter per second squared. Now, let's put everything of this into a calculator and let's find out what's the answer. We should get about 10025.4 pascals, right? Pascals is also the unit for pressure, okay? Now, let's not round this up yet. We still got a second part to do, all right? Now, let's move on to the pressure, okay? The force exerted by this bunch of liquid up here, okay? So this liquid over here exerts a pressure downwards of this many pascals. And if you remember, right, pressure is on a flat surface, okay, is also equals to force divided by area, okay? So let's do a little bit of rearranging here. We multiply both sides by area, then you get force is equals to, right, pressure multiplied by the area. Right, so pressure we didn't know is 10025.4. Okay, multiplied by the area, but what is the area? The area of this has been given here, 0.45 times 0.30, right? The area of this face over here. So let's do it this way, 0.45 multiplied by 0.30. And doing the calculations, you should get this, 1353.429 newtons. And as per usual, let's do the conversion to two significant figures. So as you can see over here, 135, right? 5 is equal to or greater than 5. So we round this whole number upwards. And thus, we should get 1400 newtons in two significant figures. Okay, so here we have our answer. All right, this is a 4-mark question, which is quite a lot for this. So let's find out how we get all 4 marks. All right, so the first mark you get is when you find out the pressure exerted by the liquid above on this area. And this is your first mark. Okay, second mark is when you, all right, write down the pressure is equals to force over area of this part. This is your second mark. Okay. The third mark is to insert all these numbers correctly. And your fourth mark is to get the answer correct here. And that is how you get your full 4 marks. Okay? Pretty straightforward, huh? Okay, good. Okay, that's great. Now let's go to question 4, part B. Second, there's water. Okay, so we are to We are shown over here, right, that figure 4.2 shows a part of a steel railway track, and there are small gaps between sections of the rail, as you can see right here. Okay, so we are to state why gaps are needed between these sections and to explain our answer in terms of particles. All right. So let's write it this way. First, let's state why gaps are needed. Okay. As you all know, railroads have gaps to allow the tracks to expand and contract without buckling the tracks, right? So let's write it down first. The gap in the rail allows the rail to expand when heated. Okay. Now here's the thing. Why does the rail expand, right? Because as in the theory of particles, right? When a object such as a solid, when it is heated, the particles inside the solid, right, they vibrate faster and harder, pushing each other apart. And that, right, that means the whole solid will take up more space as it is being heated and it expands. Okay, so let's write that down in our answer over here. Okay, explanation why this happens in terms of particles, right? So the particles in the rail vibrate faster when heated and takes up more space due to the particles pushing each other away. And this is how you get your full 2 marks, right? First mark is the statement, and your second mark is the explanation, a valid explanation, okay? Right? Now let's move on to part 3, part C. Okay, so part C shows figure 4.3 and it shows a saucepan boiling water on the heating ring of an electric cooker. Okay, and as you can see over here, the handle over here is made of plastic. So we are to explain why this material is suitable. Now, common sense, I wouldn't say it's common sense, but if you look around your house for pots and pans, right, most of the time, the handles are made of plastic or wood or some sort of thermal insulator, because when the pot is hot, right, the plastic handle or the wooden handle won't be as hot, or should I say it is cool enough for your hand to hold it, right? So why is this material suitable? It's because plastic is a poor conductor of heat. And let's write that down. Okay, this is our statement why it is good, right? Why is it usable? This is because this prevents the handle from getting too hot to touch when the pan is heated, right? So there we go. Okay, so plastic is a poor conductor of heat, and if you notice, most home pots and pans uses plastic handles, right, to allow you to hold it when it is being used over a stove. But of course, there are some exceptions where if you look for some some pans made for chefs, right, the whole handle is made of metal. This is for some other reasons, such as putting the whole pan into an oven or something like that. Okay. Right. So with that done, you get your full 2 marks. 1 mark is when you write plastic is a poor conductor of heat, and the second mark is when you write that this prevents the handle from getting too hot to hold when it's heated. That gets your second mark to get your full 2 marks for this question. Okay. with that said and done, I think we are good. This is question 4 done. And as per usual, we are 4 questions in. Do we have any questions from chat? If you do have some questions for us, please feel free to type your question in chat, and our friendly tutor, Mr. Narayan Sir, will come to your aid and we'll vet your question. And if your question is valid, I will voice it out in our video. Okay? So now there are no other questions. We can continue with question 5 of this paper. Great. Thank you, Narayan Sir, for checking there are no questions. Now, let's move on. Okay, so question 5a, part 1. Now, as you know, electromagnetic waves have many uses. So on this diagram over here, figure 5.1, we are to draw one line from each use to the region of the EM spectrum it uses. Okay, so let's go through each of this one at a time. Security marking. Honestly, I'm not too sure what this is, so let's leave it aside first, okay? Now, number 2, Bluetooth. Bluetooth, as you remember, it uses radio waves, right? So if you remember all your wireless earphones, your wireless items, or you use Bluetooth to, wait, you guys don't use Bluetooth to transfer things anymore. So yes, Bluetooth is used for things like your wireless earphones and so on and so forth. And for this, it uses radio waves. So let's draw a line downwards like this. Please pardon the crappy drawings. This is not going to be my optimum performance. I need to find a ruler. Oh wait, there it is. Let's use the ruler instead, okay? This is a bit nicer. So right here, right. Ooh, oh dear, oh dear. That's a little bit better. There we go. So yeah, Bluetooth right there. Fantastic. All right. So now, optical fibers, what do they use? Optical fibers usually uses, visual light or infrared. So let's do it this way. Infrared to optical fibers. All right. Now, next thing, detection of cancer. Right. Usually to detect cancer, we use gamma rays. So gamma rays should go down to detection of cancer. Oops. Right, here we go. Right here and down like that to detection of cancer, which leaves security markings to. Ooh, oh dear, that's really, really bad. I am terrible at drawing with a ruler here. Hang on a minute. My pen is also giving me some issues. Oh dear. Again. Oh my goodness, my pen has decided to delete itself. Second. Alright, that's better. So ultraviolet to the security marking. Okay, so let's ignore the horribly drawn thing. Give me a second. Yeah, this should be a lot better now. Yeah, that's better now. Alright. Alright, pardon for the slight issue. I think we are good for now. This pen has been around for at least 20 years. So let's move on. Alright. So let's move to 5a part 2, and we are to state one advantage of using microwave compared to radio waves to transmit mobile phone signals. As you know, radio waves. Okay, that's better. So as you know, radio waves and microwaves, right? Radio waves and microwaves are fundamentally they are part of the electromagnetic spectrum, but however, the differences are radio waves have longer wavelengths. Oh dear. They have longer wavelengths, right? While microwave has shorter wavelengths. Okay? So what that means is that, right, microwaves require shorter antenna. So if you remember, if you notice, right, last time in the past, maybe your grandparents' time, right, mobile phones look something like this, more like this, right? Big, long, antennae, right? For them to work. Okay. Oh dear, 1 second. My pen has malfunctioned horribly. One moment. Sorry for that. Okay. Right. So if you remember in the past, right? Okay, dang. Okay. In the past, mobile phones look something like this. Okay. They have long, big antennae, while currently all our phones are like just rectangular bricks like this. Okay. So what this means is, right, the antenna has become shorter. Okay. And for microwaves, right, it can actually transmit signals to satellites, right? Satellites can receive signals from Earth using microwaves, and because it is so short, right, it transmits a lot more data with a higher data rate compared to radio waves. So we can simply just write down one of these advantages. Okay, so let's just write down over here. Okay, microwaves can transfer data at at a higher rate compared to radio waves. Okay, this is just one of the many acceptable answers. The other is, of course, as I say, shorter antenna, right? You can contact, you can also contact satellites in low Earth orbit, and you can have much more data, much faster data, and much more data transferred within a certain period of time. Okay, next thing, right? So let's go to 5 part B. Okay, 5B wants you to describe the difference between transverse waves and longitudinal waves. Okay, longitudinal. Which way is correct? Please answer in. Please comment in the chat. Right? How do you pronounce this? Longitudinal waves or longitudinal waves? Let me know. Yeah. Okay. So there are several differences, and we just need one difference between each of them. Okay. So, okay, transverse waves, there are vibrations that are perpendicular. Okay, so transverse wave, this is the direction of movements. The particles move this way, perpendicular, okay? And the medium, so transverse, let me just write it down. Okay, transverse waves, the waves move up and down, and here and then while the propagation of the wave is to the right, for example. And the vibrations are perpendicular to the propagation. Okay, and next the thing is a medium may not be required because, as you know, EM waves are transverse waves as well. Okay, and some transverse waves such as EM waves can travel through vacuum, and it has peaks, which are these bits here, and troughs, which is here. Okay, so peak and troughs. Okay, now let's look at a longitudinal wave. Okay, right? So as you remember, it has compressions and rarefactions, right? So let me just draw this properly. So as you remember over here, the wave particles, right, move like this, left and right. So our wave moves this way, while the particles move left and right. So the vibrations are parallel to the propagation, and because longitudinal waves are things like sound, a medium is required for longitudinal waves, and they have compressions and rarefactions. So compressions are these, heavy spaces. This more concentrated area. Rarefactions are these so-called low pressure areas. High pressure area, low pressure areas. Okay. So we just need to, write one major difference. So let's just take all of these and we just find one that we can use. Okay. All right. So a transverse wave has vibrations that are perpendicular to its propagation. This is your first mark, for transverse wave. Now for your second mark, while a longitudinal wave, all right, has vibrations parallel to the direction of propagation. All right. And just like that, you get your full 2 marks for this question. Okay. Pretty straightforward. Yeah. Okay. Now, with that done, let's move on to 5 part C. Okay. So 5 part C. Okay. Over here, you see a simplified diagram of seismic P waves traveling through the Earth. So this is part of the syllabus, by the way. I think our textbooks do mention about seismic P waves. Okay, they are the parts of the wave that are curved. Okay, so seismic waves are produced by rock movements in earthquakes. Yeah, so as you can see here, the earthquakes here, the P waves move like this. Okay, so since the P waves, right, they are pressure waves. Okay, P waves are pressure waves that travel through the Earth. They're a bit like sound, doesn't it? So this is P waves are, technically speaking, a pressure wave and they are longitudinal. Okay, right. So now over here you see at point X, right? The P wave travels from the solid mantle. The mantle is basically this part over here. Okay, this part over here. All right, to the liquid core, which is down here. All right, let's just erase all this. Okay, and there's a sudden change in the path of the wave. As you can see here, the wave comes down here and it bends. What exactly is this, right? So if you know, the mantle is mostly solid and the core is liquid. So there's a change in medium. When there's a change in medium, you know what that means. That is refraction. Okay, so let's answer this part of the question, which is 2 marks. All right, what happened down here? So the wave undergoes a change in density of the medium. Okay, right, this is your first mark because of the change in the medium. Okay, change in density of the medium. This changes the wave speed and it undergoes refraction. Okay, and just like that, okay, there we go. It changes the speed and undergoes refraction. Straightforward, yeah? First mark goes when you write down the wave goes through a change in the density of the medium. That's your first mark. Second mark is when it undergoes refraction. That gives you your full 2 marks. Okay. Excuse me, let me get some water. All right, so now let's go to part D. D states, right, that the Earth's surface absorbs incoming radiation from the sun and also emits thermal radiation from its surface. And over the past 50 years, scientists estimate that the average temperature of the Earth's surface has increased approximately by 0.75 degrees Celsius. So explain what is causing this average temperature rise. All right. So the first thing that probably comes to your mind is, everybody, this is a hot topic even till today, and I know some people deny it, but this is true. There's something called global warming or climate change, right? This is real. And during the last 50 years, right, yes, the temperature of the Earth has increased. And how does it happen? This happens due to something called the increase in carbon dioxide or greenhouse gases. So what does greenhouse gases do? Well, they trap radiation in our atmosphere and it prevents radiation from escaping into space, and that warms the Earth, right? So pretty much, right, the past 50 years, the temperature increased due to human activity, releasing CO2 in the atmosphere and greenhouse gases in the atmosphere. And this extra greenhouse gas traps radiation much more effectively and prevents this radiation from escaping into space. And thus, this warms the Earth. And with that, let's write down the answer over here. All right. The temperature rise is due to the increase in carbon dioxide and okay, that's not just that. Carbon dioxide emitted into the atmosphere. This is your first mark. Okay. Right, a second mark should be this. The carbon dioxide, as stated here, traps radiation in the atmosphere and prevents radiation from escaping. Okay, which causes the Earth's temperature to rise. Right, just remember, right, although the question, the marking scheme writes your answers in bullet form, you are to write your answers in proper English sentences. Okay, so this is what you must do. Okay, right. Okay, now that is done, let's move on to question number 6. Now 6 over here shows a circuit. Yeah, finally we move on to the electrical circuits. And this circuit shows an LDR. What exactly is an LDR? It is a light-dependent resistor. So when light intensity increases, right? Okay, sorry. When light intensity falls, resistance of an LDR increases. So when there's light, right? LDR increases. Okay, sorry. When there's light, LDR decrease in the resistance, and when there is no light, LDR increases in resistance. Okay, right. So now this LDR is in a brightly lit room, and the voltmeter over here, which is connected in parallel, reads 1.8 volts. So the potential difference across this LDR is 1.8 volts. So we are to calculate the current in the 400 ohm resistor. The current, right? So as you know, the current of the 400 ohm resistor, since it's connected in circuit, is also the current for this whole entire circuit. Okay? Now let's take a look at this, okay? First things first, we need to find the potential difference across this 400 ohm resistor. We already given over here, this is 1.8 volts across the LDR. So first find voltage, not voltage, but we should put potential difference across 400 ohm resistor. My bad. Let me just write this properly. Will be equals to the total potential difference of this circuit minus the potential difference across the LDR. So it's 5.0 volts minus 1.8 volts, and that gets you 3.2 volts. Okay? Now, we can find the current across this 400 ohm resistor. So we already given the resistance here. P is equals to, oh sorry, my bad. So if you remember the equation, V equals to IR, and you want to find the current, so you divide both sides by R, you get I is equals to V over R. So let's write that down. The V over R, right? Okay. And it should be equals to 3.2, which is the voltage, divided by R, which is 400 ohms. Doing the calculations, you should get 0. Wow, there's a lot of zeros. 0.0080 amperes. And just nice, this is in two significant figures. Okay? Let's write it down nicely. 0.0080 amperes. You can also write this as 1, 2, 3, 8 milliamperes. 8.0 milliamperes, my bad. It should be also equals to 8.0 milliamperes. Optional, but this is doable as well, okay? So, to get your full 3 marks of this question, first you must find the potential difference across the 400 ohm resistor. This gives you your first mark, okay? Second mark is if you can state this equation, and the third mark, if you can find the correct answer. Okay, this works as well, huh? All right. Now, let's move on to 6a part 2, right? 6a part 2 states that the light level of the room changes from bright to dark, and we are to state and explain the effect on the voltmeter reading. Now, just now as we have described, right, for an LDR, a light-dependent resistor, when it is bright, the LDR should have low resistance, and when it's dark, right, when it's dark, the LDR has a higher resistance. Okay? So, what does that mean? When the resistance of the LDR increases, right? Let's say at first maybe it's 100 ohms when it is bright, but when it's dark, maybe let's say it's 500 ohms, right? So the voltage across this LDR should also increase. Okay, let's write down. So the voltmeter reading increases. Now, why is that so? Now, let's just write down what we have discussed earlier. Number 1, all right, when light intensity falls, the resistance of the LDR increases. That would be your first explanation mark. Second explanation mark, since the ratio of the potential differences across the potential divider and resistor is dependent on the ratio of their resistances. When the resistance of the LDR increases, the potential difference should rise as well. Okay. potential. There we go. There we go. All right. So basically, what this means is, as you seen earlier, when the light intensity falls, resistance of the LEDR should increase. All right. So because, right, the ratio of potential difference across the potential divider and resistor, so these two, right, the ratio is dependent on the ratio of their resistances, right? So if this resistor has an increase in its resistance, the potential difference across it should also increase. Okay. All right. So this is your first mark. This is your second mark. This is your third mark to have a full 3 mark for this one. This is a little bit tougher, so I won't blame you guys if you don't really know how to answer this. But if you want to, learn how to do this better, you can go to our homeschool.asia website to pick up on this particular part. All right, this is video 4.14, and if I'm not wrong, I wrote this one. Okay, so I actually created this video, so please have a look if you have a chance. All right, so please remember, Homeschool.asia, if you're not sure how to answer these kind of questions, we have videos on how to solve these. We also have videos what exactly is going on, teaching you all the basics you need to know. Okay, right, let's move on to part B. Okay. All right, so part B, you see two LEDs or light emitting diodes connected in parallel to us in a circuit. And R is the red LED and G is the green LED. And the voltmeter across these LEDs show a potential difference of 2 volts. Okay, so this can be a little bit, difficult for you guys to see what's going on. So let me just draw this in a much more, intuitive way to do it. So our red LED and our green LED, okay, they are connected in parallel, okay, like this, okay, like that, okay, and this is connected to plus, minus, like this, okay, and of course the whole thing is connected in parallel, right, with, like that, connected with a voltmeter right there in parallel with everyone. So the voltmeter measures the combined potential difference of these two, okay, 2.0 volts. All right. So as you can see over here in the graph here, this shows a potential difference graph for the LEDs, right? So we are to use figure 6.3 to determine the current in the ammeter. Where is the ammeter? The ammeter is right here, connected in series with this resistor and connected in series with these two connected in parallel. Okay. Oh, I'm so sorry. This is covered by my face. Take a look here. Okay. This is a lot better, right? Okay. So this is the diagram. Okay. As we see, the red and green LEDs are connected in parallel, okay? And the voltmeter is measuring their combined resistance, which is 2 volts, okay? So, first, let's use figure 6.3, which is this graph over here, to determine the current in the ammeter. How do we do that? Okay? So, first things first, let's take a look at the graph. So first things first, let's draw a vertical line from 2 volts, which is where we will be starting our reading. So it's right up here, 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 and ping pong. Oh my goodness, this is bad. Sorry, let's try this again. My drawing skills are not the best, especially on the drawing pad, so hang on a moment. Sorry, like this, okay? This is a very bad example. Let me try again. Please draw straight. Much better. Much better. So 2.0. Now you see it intersects the green LED here and the red LED here. Okay? So from the green LED, you see this is 10 milliamps. So 1 unit up, this is in 2 milliamps each. So this is 12 milliamps here. And over here is 44 milliamps here. Okay? So first thing, let's write down. Okay? Current of green LED is equals to 12 milliamps, as we have seen over here. And the current of red LED is equals to 44 milliamperes, as we have seen up here. Okay? So, now that it's done, we know the total current of a circuit is basically the addition of all the branches, the individual currents of each individual branch. So if this is 44 milliamperes, this is 12 milliamperes, the total current should be addition of both. Is equals to 12 plus 44. Okay? And that should give you 56 milliamperes. Right? So let's write that down. 56 milliamperes. Okay? And that is your full 2 marks. How do you do so? First thing, you must have these two parts correct. This is your first mark. And secondly, you must know that the total current is equals to these two branches added together, and that's your second mark. Okay? Now, for part 2, the connections to the power supply is now reversed. State the reading on the ammeter. So now, this becomes minus and this becomes plus. So, as you do know, for a light emitting diode or any diode of any time, right, current only flows in one direction. So now, since the current flows in the opposite direction, the current cannot flow over here. So since there's no current flowing, the current of this whole circuit should be simply 0 milliamperes. Okay? Right, because do take note, a diode or light emitting diode only allows current to flow in this direction. Okay? But in the opposite direction is no go. Okay? 0 amperes. Or 0 milliamperes, whichever that you prefer. Alright, so far so good. Now question 6 is done. Do we have any other questions from the chat? None? Okay, now let's continue with question number 7. Alright, let's speed this up a little bit. We are almost done. We are 6 questions in, 4 more to go. Right, so question 7, we show a simple AC generator like this, okay? Remember, this is an AC generator, not a DC motor, okay? So an AC generator, right, you should have a magnetic field over here. You should have 2 slip rings and you have a circuit over here, alright? So we are to explain the function of the slip rings and the brushes. So what do they do? So as you can see, these slip rings, right, they provide a constant contact of the coil to the circuit, alright? And the brushes are used to connect the slip rings electronically, alright? So let's write that down. Okay, text time. The slip rings and brushes provide continuous connection between the coil and the circuit of to the lamp. Okie dokie. All right, so with that done, we have one part done. All right, so with just like that, 1 mark. Very nice. Okay, next, we should go to A part 2. Describe how an alternating current is generated in the lamp. All right, so as you know over here, an AC generator, as the name suggests, it generates an alternating current, and we are to explain how this works. So let's write this down quickly. So firstly, when the coil rotates in the magnetic field, okay, the wire cuts through the field and induces an EMF. What should I say? An electromotive force, bracket EMF. Okay, so this is the first point. Actually, this point contains 2 points. So let's continue with the next part. Just write this thing properly so that it can be stored nicely. Okay, next, right? When the coil turns 180 degrees, the current induces changes to the opposite direction. All right. And that is how you should write this, how you should answer this question. So, surprisingly, this is very short, right? How so? So, as you can see here, there is a magnetic field from north to south here, right? Okay. And when this coil moves upwards, it cuts the magnetic field perpendicularly. So it generates, using your Fleming's left-hand rule, right? It should generate, let's see, a magnetic field to the right, which is pointing this way with your index finger. The motion is upwards, which is like this, and the current is pointing towards you. So the current should move this way, right? When it moves here. So it keeps moving upwards, right? To here, you should, when this part of the coil is moving upwards, so basically when it moves from here to here to here, right, it keeps moving upwards, and it should generate a current moving towards you. But when this coil moves to the other side, it moves downwards right now. Okay, so when it moves downwards, right, let's use Fleming's left-hand rule again. So Fleming's left-hand rule, the current is what we need to find over here. The magnetic field is to the right over here, but now the motion is moving downwards. Okay, now when you're moving downwards, okay, the current is now moving. I'm so sorry. Thank you for saying this. Fleming's right-hand rule. I'm so sorry about that. Thank you, Naran sir. Thanks for reminding me of Fleming's left and right-hand rule. So let me just correct myself here a little bit. Thank you so much. That is embarrassing. I forgot my left hand and right hand rule. Okay, so using Fleming's right hand rule, let's do the left side again. So doing this left side, your okay, during this left side, right, your motion is moving upwards. So your finger, your thumb should be moving upwards. Your index finger, which is the magnetic direction, should be moving to the right. So your current, which is your middle finger, points into the screen, and thus the current moves into the screen like this. Okay, this direction. And then when your coil moves over to the other side, okay? When your coil moves over to the other side, the same thing happens. You're using Fleming's right-hand rule, your motion is downwards, while your direction, which is your magnetic field, points to the right, which is this direction. Okay, this is now a bit difficult to see. And the current now points towards you. So at this part, the current moves in this direction. Okay? So for this, every half a turn, right, the current changes in direction. Okay? Okay, so as you can see here, the current moves in this direction and moves this way and this way for when it moves this direction. Okay? Oh. How did I... Alright, so that's that. Okay. Am I right saying this correctly? The coil turns 180 degrees, the current induces changes to the opposite direction. Yep. So pretty much that. So do take note, right? In using Fleming's left-hand rule, as I stated earlier, is wrong. Fleming's left-hand rule is for the DC motor. As for Fleming's right-hand rule is used for an AC generator when it's used to induce a current. Okay? So that's that. So, okay. Over there. All right. Okay. All right. Give me a second. I need to quickly check a few things. I'll be right back. All right. Sorry for the slight delay. I need to clarify some things with my tutor. Okay. So basically, as this current, okay, as you see, right, this is the current of this particular part of the wire right now. When the coil goes upwards, right, the current is this direction. But as this coil moves over to the other side, right, same coil, right, the current induced now moves on the opposite direction, like that. So, oops, my bad. The coil goes in this direction. So, as you can see over here, every half of a turn, right, the current induced, like this, right, changes. And because of that, the current produced by this AC generator looks more like this. Okay? This is 180 degrees. This is 360 degrees. This is the positive current. This is current. And this is the negative current. Like that. And that is how you get an alternating current generated through this circuit. Okay? Right? And now let's move on to A part 3. Now we are to state two possible changes to cause a larger maximum current in the lamp. Of course, the easiest method is, to spin the whole thing faster, or spin the handle faster so that it generates a greater, motion. It cuts through the magnetic field faster and it generates a greater current. Or number two, you can also increase the magnetic field strength of the two magnets over here. So Method number 1, spin the thing faster. Method number 2, stronger magnetic field. Method number 3, increase the number of turns in the coil. So currently, as you see in this coil, is only probably one coil. But if you increase this by many times, you increase, the effect of this movement, and you get a greater current. So these are 3 methods you can use. All right. So let's write down the first 2 that I have mentioned earlier. 1 second. All right. Looks like we have a slight disturbance. We have a lion dance near my place. So anyway, let's continue how to write this. So we have stronger magnets for a stronger magnetic field. This is our first possible answer. Second possible answer is we can increase the speed of rotation of the coil. So either of these or the increased number of turns of the coil should cause a larger maximum current in the lamp, right? Okay, now let's move on. Very good. Okay, now let's go on to, what's this part again? This is 7 part B, okay? 7 part B. This is a graph to show how the EMF varies with time for the coil. As we've seen before, the EMF goes up, goes down, goes up, goes down in a sine wave like this, right? This is alternating current after all. So we have to determine how many revolutions the coil has made from time 0 to E over here. So from our basic knowledge, when the graph undergoes a full period, it goes up like this, down like this to here. This is considered 1 turn. Okay, so here's 1 turn, 2 turns, and this is 1/4, right? So this is not 1/4, this is another half a turn. So we should say it goes through 2.5 turns. Okay, 2.5. Okay, good. So it goes through 2.5 turns. Easy, right? Let me just write this nicer so it's a bit nicer for you guys. All right. Now let's move on to part 2. Excuse me. So figure 7.3 shows the end view of the position of the plane of the coil at time 0, right? So the coil is rotating anti-clockwise. So as you can see over here, right? Let me just draw this a bit nicer so you guys can see. This is the north. This is the south. Okay? And the coil is currently looking a bit like this. Okay? And this is the outwards. Okay? It should turn like this. It should turn like this and like this. Okay, this is side view. Okay? Okay, so we are to draw 4 lines to match the coil position to times A, B, C, D, as we have seen up here, A, B, C, D, okay? Right, then we have to match the positions here. Okay, each coil position may be used once, more than once, or none at all. So basically, we can have 2 of these pointing to the same one, okay? Oops. All right, so now let's check position A. Position A is right here. It is at the maximum EMF, right? For the coil to be at maximum, okay, right, it should be something like this. It's moving this. It should be directly the movement of the coil at the end should be directly perpendicular, right, to the magnetic field. Okay, so for A, we are very sure it should go to this. Okay, right. Now let's go to take a look at B. right? B over here is 0. It has 0, it is now 0, 0 EMF here. This is when the coil is directly vertical, and when it's directly vertical like this, right, its movement is parallel to the magnetic field and there is no current generated. So B very likely, most likely, is going to the last one. Okay? Now C, part C. C is also a 0. Okay? Now there's 0, there's no EMF produced here. So C should have the same as D. Alright? And finally, part D is at the bottom here. Also another, this is the minimum of there. And for this to happen, it also should have the same arrangement of the coil like A. So when the coil is vertically, vertical, it is horizontal, right? As it moves, right, it cuts across more magnetic fields as it moves. So it's perpendicular to the magnetic field. And with that, it has the maximum or minimum as well. So let's draw a line like this. And this should be your answer. Okay? Very straightforward, yeah? Okay? So, in short, A and D has the highest EMF, so the coil should be perpendicular to the magnetic field. While B and C has 0 EMF, so the coil should be parallel. The coil should move parallel to the magnetic field like this over here. It should move this way, it should move this way, while the magnetic field is this way. Okay? So hope this one helps you in your explanation. Okay? This should be the magnetic field. Okay, good. Let's move on. Now, part 8. No, question 8, all right? Whoa, we are almost 2 hours in. Let's quickly move, all right? So alpha particles are directed at a very thin sheet of gold foil, and the following observations provide evidence for a nuclear model of the atom. If you guys know this is called the Rutherford experiment, right? Rutherford's experiment, right? So state what the conclusions may be made about the model of the atom through these observations. Okay, so Rutherford's the particle scattering experiment shows, right, that the observation is that most of the particles pass through the foil. As you remember, this is how the gold thing looks like, and there's like a very tiny atom in the center. Most of the alpha particles just pass straight through like this. So if most of the alpha particles pass straight through, we can say that the conclusion is most of the atom is made of empty space, right? And that is the thing. Another option to say is the nucleus is also much smaller than the atom, right? And now observation 2 suggests that a few particles bounce back or deflected in very large angles like this. Excuse me. So, alpha particles, as you do know, are positively charged. So for them to bounce back or deflected through large angles like this, it can only show that the nucleus has a positive charge. Excuse me. Okay. That repels the particles, the alpha particles. The Rutherford's experiment is pretty much like this. Okay, so there you go, 1 mark each for the correct explanations. Now let's move on to part B. Okay, part B shows 3 beams of ionic radiation, alpha, beta, and gamma passing through 2 parallel plates, like this charged plate, okay? The plates are charged and there's a uniform electric field between them. So the uniform electric field is straight, okay? Now, first we are to state and explain which path is PQR shows the beam of alpha particles. Alright. Now we can see, right, Q goes all the way straight. So, as you do know, gamma rays are the rays that are not affected by a charged particle. So this is definitely the gamma ray. Alright? Excuse me? Excuse me. Now we are left with the P and R. So, alpha particles are made up of 2 protons and 2 neutrons. Okay? While an beta particle is made up of an electron, which has much less mass compared to the alpha particle, right? This is a chunker. It's very, very heavy. So that means, right, if we were to put the alpha particle and the beta particle through a charge plate, remember, alpha particle has a +2 charge, but it is so heavy, it is so much heavier that it is affected much less compared to a beta particle. Alright? So we are very sure P is the alpha particle and R is the beta particle. Okay? So let's write that down. The path is P, and the explanation is because alpha particles are heavy, they are chunkers. Okay, so alpha particles has much greater mass than beta particles, so they deflect less than beta particles. Okay, so they deflect less. Right, here we go. Very straightforward, yeah? Now let's move on to this. Okay, we have to state and explain the direction of the electric field between the plates. Right, so alpha particles have a charge of +2. Beta particles have a charge of -1. Okay, now you see the beta particle moves downwards, which means the minus charge is attracted to the positively charged plate at the bottom, while the alpha particle is deflected by this positively charged plate and attracted to the negatively charged plate on top here. So the electric field should be going this way. Okay, upwards like that. Okay, with that done, okay, with that done, let's write it down. So the direction is upwards. And the answer to this is, okay, this is because the alpha particles are deflected upwards. So they are repelled by the negatively charged bottom. By the positively charged bottom plate and attracted to the negatively charged top plate. Now that's done. And that's your 1 mark. Wow, right, so much for 1 mark. Okay. Alright, so let's move on to part C. Alright, so part C states that curium-242 is a radioactive isotope and it emits alpha particles and it has a half-life of 160 days. Right, so after 480 days, the mass of curium-242 in a sample is 2.4 times 10 to the power of minus 3 grams, and we have to calculate the initial mass of curium-242 in the sample. Okay, so let's just write a few things down first. So one half-life is about how many again? 160 days, right? So one half-life is 160 days. So if we have 480 days, it should be equal to 480 divided by 160 should be equals to 3 half lives. Oops, pardon my spelling. Right, okay, this will get you your first mark for this question, okay? Now, let's move on to here. Okay, so now we have to take note of this, right? The number of atoms, right? Or should I say the mass of the atoms, okay, at any time is equals to the mass or number of atoms in the beginning, right? Right, multiplied by half to the power, okay, of t over t half. Time and the half of the half-life here, okay? All right, so we already have this, which is at 480 days, this is equals to 2.4. 2.4 times 10 to the power of 3 grams is equals to n naught, okay, half, and this is 3 half-lives. 3 half-lives should be like this, power 3, okay? So now, let's do this. Let's move this over to the other side so we can find n naught. N naught should be equals to 3.4 times 10 to the power of 3, okay, divided by half to the power of 3, which is equals to, half the power of 3 is actually equals to 1/8, right? So 2.4 times 10 to the power of minus 3 divided by 1/8, which is also equals to 1.92 times 10 to the power of 2, right, grams. Now let's turn this thing into two significant figures. We look 1, 2. 2 is less than 5, so we should get 1.9 times 10 to the power of minus 2 grams. Then this is your initial mass, okay? 1.9 times 10 to the power of 2. And remember to write grams, okay? So getting this correct gets you your second mark, okay? Actually, I'm my bad. I think this should actually get you your first mark, okay? All right, so with that, we are done with, oh my goodness, we are done with part C. And done with question 8 as general. All right, so far there's no other questions. Now let's move on to question number 9. Okay, question number 9 wants you to state, right, when is the CMBR or cosmic microwave background radiation, when is it produced? Okay, right, and it can be observed from every direction in space. So state when is CMBR produced? Well, pretty sure this one you guys have remembered if you studied the astronomy part well. The CMBR is shortly produced after the Big Bang. Right. Okay. Right. So this is microwave background radiation, right? And why do we observe microwave instead? So pretty much, right, simply put, right, the original wavelength is infrared or light and a visible light. But because, right, this wavelength has increased so much due to being redshifted due to our universe expanding so much, and that's the reason why the wavelength of this particular radiation has redshifted from infrared to microwaves, and that's why it's called cosmic microwave background radiation. Okay, let me just write that down. Okay, the wavelength has increased because the universe has expanded and the wavelength is redshifted. Okay, 2 marks for this question. Okay, first mark is when you write wavelength has increased because, and the second mark is because the universe has expanded and wavelength has been redshifted. 2 marks. So that gets you your full 2 marks. Okay. Now let's move on to table 9.1. And table 9.1 shows about the planets in our solar system. We got Venus, Earth, Jupiter, and Jupiter, Saturn, and Mars. And we have the planets, the average radius of the orbit around the sun, time taken for one orbit, and the average surface temperature in degrees Celsius. So, let's take a look here. The orbit of Venus is approximately circular, and we are to calculate the average orbital speed v of Venus, and we are to give our answer in kilometers per hour. All right, so orbital speed is pretty straightforward, yeah? Okay, orbital speed is this. Is equals to, right, 2 pi r divided by t. And you have to first make sure t is in hours, okay? Make sure t is in hours. And 2 pi r. R is basically the radius of the planet, which is here, 108, and pi. So let's do it this way. 2 pi times 108 times 10 to the power of 6, okay? Divided by the orbital speed here in orbital speed here, t. So time taken for Earth orbit is 0.62 years. So 0.62 years multiplied by 365 multiplied by 24 hours, because you want the answer in kilometers per hour. Okay, so hours, yeah. And doing the mathematics, right, we should get this huge number, 124,941 times a 0.82, which gives you in two significant figures, 1, 2. 4 is lower than 5, so we round downwards. 1.2 times 1, 2, 3, 4, 5. So 10 to the power of 5 kilometers per hour. All right. So I'm now doing this in standard form, so there's less to write. Okay. Remember, 1.2 times 10 to the power of 5 over here. Okay. that should give you your markings. Please remember to write this in two significant figures as well. Yeah? Okay? Okay. So, let's move on to part 2 of this question, 9a part 2. So state, is it 9a? Is it 9b? 9b part 2, sorry. All right. So next, we are to state how the average surface temperature of a planet changes as its distance from the sun increases. Okay. Okay, so there we go. How the average temperature of a planet changes as its distance from the sun increases. So as you see over here, Venus is the closest to the sun, right? And it's the hottest. While Saturn is the furthest from the sun and it's the coldest. So we can draw a pretty straightforward conclusion over here, right? As a planet, as a planet is further away from the sun, okay, as a planet increases its distance from the sun, okay, the average surface temperature decreases. Okay, there we go. Okay, very good. All good, yeah? Okay, fantastic. Now that is done, let's move on to question 10. We are in the last question for today. Yeah. All right, so now we are to sketch a diagram to show the orbital path of a comet around the sun. Right, and we are to mark the position of the sun on your diagram using an S. Okay? So, if you know the pathway of a comet, right? A comet it goes around the sun in a very highly elliptical orbit. So first, let's draw a very elliptical orbit. Please don't mind this, okay? This is very badly done. Let me try again. Okay, it should be nice, more elliptical than that. That should be a bit sharper, but please don't mind this, okay? And then the comet orbits around here, and of course the sun should be somewhere around here, on one end of the ellipse, okay? Now, this is the first mark, okay? The first 2 marks. So the thing is, this is a 2-mark question. So as long as you draw an ellipse like this, and you put the sun on one end like this, you should get your full 2 marks. Okay, part B, the question wants you to draw where the comet is traveling with the slower speed, okay, on this orbit. Of course, the comet travels the slowest when it's the furthest away from the sun, which is here. And this should be marked L, okay? Right, so pretty simple, right? This is where the comet is slowest, here's where the comet is the fastest, conversely. So, part C, we are to explain, right, why the speed of the comet changes as it travels around its orbit. And we have to use the conservation of energy in your explanation, right? So let's go back to our diagram over here once again, okay? So when the comet is furthest away from the sun, right, it has the greatest gravitational potential energy, right? It's the furthest away from the sun. And when it is closest to the sun over here, it has the lowest gravitational potential energy, but the greatest kinetic energy. Okay? Conversely, when the comet is far away from the sun, it has lowest kinetic energy, so it travels really slowly. When it's over here, where the comet is, it has a nice big long tail and it moves really, really fast along the sun here. Okay, so we can say that when the comet is on its furthest away from the sun, it has the highest gravitational potential energy, and lowers kinetic energy. As it moves closer to the sun, the gravitational potential energy is converted into kinetic energy. Okay? Pretty straightforward, yeah? So let's explain this nicely in words. Okay? First things first, the total energy of the comet is equal to the sum of gravitational potential energy and kinetic energy of the comet. Okay, that's our first mark. Now for our second mark, let's write, as the comet approaches the sun, okay, its gravitational potential energy is converted into kinetic energy. Right? That's very good. Oops. This down a little bit. And then finally, thus the comet has greater kinetic energy and it moves faster as it gets closer to the sun. And simply like that, we have our 3-mark question done. Okay, so first mark is when you mention the total energy of a comet is equal to the sum of its gravitational potential energy and kinetic energy of the comet. Second mark is when you say the comet is close to the sun. Okay, sorry, 1 second. Is when a comet approaches the sun, its gravitational potential energy is converted into kinetic energy. And finally, the final mark you will get is when you say the comet has greater kinetic energy as it gets closer to the sun and thus it moves faster. Okay? With that done, that gives you your full 3 marks. Okay? So 1 mark here, 1 mark here, and final mark here. Okay? And with that, we are done. We're done with this paper. All right. So, okay, I guess that is it for now. And once again, I'd like to ask chat, do you guys have any other questions for me? Please go ahead and write it down in the comment section or in chat as well. My very helpful teacher, Mr. Narayan sir, will look through your questions. We'll answer them with our best abilities. Yeah. So let's take a look here. Okay. Okay, so far no other questions. Okay, good. Narayan sir, do you have any other questions from the chat? Okay, thank you so much, sir. Thank you so much, Narayan sir. And no other questions up to now. Fantastic. Okay, in that case, I think we can call it wraps for now. All right, fantastic. So we are done with today's question. All right. Thank you, Narayan sir. Thanks for the confirmation. No questions now. All right. So we are done for today. Okay. And all right. So once again, thank you so much for joining us in this session for solving the IGCSE papers live. And I'm glad to be here with you guys and solving papers together. And if you guys have any other questions, please feel free to comment in the chat section below. Or if you'd like to find out what we do over here, you can check out homeschool.asia, where you have the best education videos for IGCSEs and the A-levels. Or you can also check out CIE.papers for CIEpapers.co for the most up-to-date recent Cambridge papers that are released. So with that done, thank you so much for being a fantastic audience. Thank you, Naran sir, for being there with us all the way to the end. And wish you all good luck, good night. Goodbye. Okay, I think we are done.